Okay, so you've noticed that when you've been doing the probability problems, we've been doing probabilities of a single event every time. So probability of drawing a 4, probability of whatever else we've been doing. So what we want to now do is we want to kind of transition to be able to do slightly more intricate things. I'm not going to say complicated because, again, if you can take a basic probability, you can do any of the things that we're going to be talking about. So we want to go ahead and be able to take the probability of multiple events. So before we can get there, we need something called the counting principle. Okay, this is one of the fundamental rules in probability. And what the counting principle says is this: if a first experiment has m distinct outcomes, so m is just the number of outcomes. So for instance, if I flip a coin, how many outcomes are there? 2. Okay, so that's what m is referring to, the number of outcomes. If I roll a die, how many outcomes are there? 6. Okay, so if you do a first experiment and it has m outcomes, and then you do a second experiment that has its own set of distinct outcomes, n, then when you do the two things together, in that specific order, they have m times n distinct outcomes. So for instance, let's put some numbers to this so that it seems a little more reasonable. So my first example says, how many possible outcomes are there when a coin is flipped and then a die is rolled? Okay, so you've already answered this question individually. Now we're going to put it together. So you told me how many outcomes when the coin is flipped? 2. Then you'd multiply. How many outcomes when a die is rolled? 6. And so that means when I do those two things together, if I'm up here on the table and I flip a coin and roll a die, then there are 12 possible outcomes that I could have. So right below that, I didn't put this on there, but let's go ahead and let me ask you to do one real quick. Let's just say, how many possible outcomes are there when you roll two dice? Okay, so you roll the first die and then you roll a second die. So what I want you to do is use the counting principle to determine how many possible outcomes are there when you roll 2 dice. Okay, how many outcomes are there when you roll the first die? 6. How many outcomes are there when you roll the second die? 6. So when you do it together, okay, when you're playing Monopoly and you're using 2 dice, okay, then there are 36 possible things that can happen when you roll those 2 dice together. Now, I don't know how familiar with board games you are, but if we then talked about like Yahtzee, where you roll 5 dice, okay, well, we could do this. It just doesn't have to be for 2 times. What are the possible outcomes if I roll 5 dice? Well, then you would just do that 5 times. The number of outcomes for the first die would be 6. The number of outcomes for the second one would be 6. How many for the third one? Yep, and for the fourth one, 6, and for the fifth one, 6. So if you like that game, if you even know what I'm talking about, I know I'm old school. So if you like that game, when you roll, oh, I don't know what I pushed, 6 times 6. 3, 4, 5. When you roll the 5 dice in Yahtzee, there are 7,776 possible things that could happen when in your outcomes. Okay, so there's a lot of possible outcomes. That's what the counting principle is doing for us. Example 2. The reason I have this example here is because you have to get to know in the rest of this chapter what the terms with replacement and without replacement mean. Okay, they're giving you a distinction between how you are performing an experiment. Okay, so for instance, if 2 cards are drawn from a standard 52 card deck, so it's just the deck of cards, you don't need the picture here because the pictures, we're not dealing with any specific cards, but if you're going to draw 2 from a 52 card deck, how many possible outcomes if they're drawn with replacement? Now, here's what with replacement means. I draw the first card, I look at it, whatever it is, and then what do you think I do with that card? I'm going to put it back. It's eligible to be drawn again. Okay, so with replacement means I replace the card, then I shuffle them, and then I draw again. Okay, so with replacement, how many cards are eligible to be drawn the first time I draw? 52. Times, I pull the card out, I look at it, it is whatever it is, then I put it back. How many cards are eligible to be drawn the second time? 52. So that means when I draw 2 cards from a deck of 52 cards, and I do that with replacement, then that means that there are 52 times 52. That is 2,704 possible combinations of cards that you could draw. All right, well, now you don't always do things with replacement. Probably the more realistic example is without replacement. So what without replacement, those words mean is you pull the first card, you look at it, you see what it is, then what do you think you do with it? You put it away, you put it somewhere else, you keep it, okay? You're not putting it back in the deck. Okay, so without replacement means how many cards are eligible for the first card that I draw? 52. Now, I'm not replacing that card. I'm doing this without replacement. How many cards are eligible for the second one? 51. There you go. And then if we did this another time, a third time, in fact, I think that might be what I'm going to have you do here, because I don't have as many problems for you as I thought I should when I made this sheet. So 52 times 51 is equal to 2,652. So notice the total number of possible combinations goes down slightly. Well, let's do this. I'm just going to draw a little line right here. So instead of doing this for 2 cards, but I want you to use the counting principle. I want you to do each of these 2 problems again with replacement, without replacement, but this time we're drawing 3 cards. Okay, and I would like you to go ahead and tell me how many possible outcomes are there when I draw 3 cards. First, when I do it with replacement. Second, when I do it without replacement. All right, so I'm drawing 3 cards. When I first do it with replacement, let's just go through. For the first card, how many options are there? 52. I'm doing this with replacement. How many options are there for the second card? And then finally, I do this with replacement. How many options are there for the third card? Fantastic. Well done. I appreciate your helping me out. So 52 times 52 times 52. Did we all get, wow, that's a lot of options. 140,608. That's the number of combinations of 3 cards you can get when you do that. All right, well, now let's do it without replacement. So again, I'm going to start you off. There's 52 cards the first time. Then you're not replacing that card. So how many do you have for the second time? 51. And then you're not replacing that card. So how many do you have for the third time? Perfect. And on and on. If we drew 4 cards, you keep going. Everybody following along the pattern that's going on there? Okay, if you understand the distinction between those 2 words, that's going to be really helpful as we go through the rest of this unit. So 52 times 51 times 50 is equal to 132,600. Great. Well, the counting principle is something that we will come back to and use several different times as we go through the rest of this chapter. What we're going to do now, related to the counting principle, say, okay, I've told you what the counting principle is. Let's now say that I want to make a list of all of those possible outcomes. Now, we're clearly not going to do it for these problems. That's way too many. But let's just say for this, my flipping a coin and rolling a die. I want to have a procedure that I'm going to be able to have all of the possible outcomes. Well, that's the procedure that we're going to use is called making a tree diagram. Okay, we're making a tree diagram. And here's how you make a tree diagram. So for example 3, I'm going to do just this. I'm going to do a tree diagram when I flip 2 coins. Okay, so I'm taking the fairly simple example. Then in example 4, I'm going to have you do the tree diagram for flipping a coin and rolling a die. So I'm flipping 2 coins. So we're going to do first coin, second coin. So here's my seed of my tree. My tree is actually going to grow sideways. Okay, just because that's where I left my room. If you wanted to do this up and down, that's totally fine. Okay, so this seed represents my first thing, my first coin. What are the options when I flip the coin? I can get what? I can get a head or a tail. So here you do. Here's what you do. You draw a branch for each of those outcomes. So I'm going to draw a branch for the outcome of heads. I'm going to draw a branch for the outcome of tails. Okay, so that's my first coin. You with me so far? Okay, well, I'm just going to cover up the bottom branch for a second. Let's just pretend that my first coin was a heads. I'm going to now flip the second coin. What are the possible outcomes when I flip the second coin? Heads or tails. So from there, I'm going to draw 2 new branches. Okay, so from here, my second coin could be a heads or it could be a tails. Okay, I'm going to cover up the top branch. And we're going to look at, well, my finger's just now in the way, sorry. Now we're going to look at the bottom one. And so this is now the option, I got a tails the first time. Okay, so then what are the possible options when I flip my second coin here? Heads or tails again. So there's all the branches representing my second coin. If I had given us the option to do 3 coins, then we would just do the whole thing again. And maybe we'll do that on the back. By the way, if you remember when we did truth tables, and we did truth tables for when we had 3 simple statements and we had to do 8 rows, those 8 rows are just generated by doing a quick tree diagram of trues and falses. The first statement can be true or false, and then you do trues and falses for the second and trues and falses for the third. And that's where those 8 statements came from. And so what we're going to do now is we're going to list out all of those outcomes. We're going to be a squirrel. We're going to run on those branches. This is called the sample space. So if these words are used in your homework, the sample space is just the list of all the possible outcomes. So here we go. For no particular reason, I'm just going to do the top branch first. So as I follow the branches, the first outcome is a heads, then a heads. So HH. The second outcome is HT, heads, tails. So the first outcome is the first coin's a head, the second coin's a heads. The second one's that first coin's a head, second one's a tail. Then the bottom branches, first coin's a tails, second's a heads. And then finally, tails, tails. Now I understand you probably could have generated that without doing the tree diagram because it's just 2 flips of a coin and there's only 4 outcomes. But I wanted to show you that because gradually the things we're going to do are going to get a little more complicated. So I would like you to give your best attempt. Okay, if you don't get this first one, that's okay. We're going to do another one. Use a tree diagram to list all the possible outcomes when you flip a coin. So your first 2 branches are going to look just like my first 2. But then instead of these heads and tails branches, you're going to roll a die. Okay, so give it a try, see how you do, and then we'll adjust. All right, so confirm and then ask any questions you need to, okay? Because once you can do this, there's no mystery to tree diagrams. You can do any tree diagram. So we flip a coin, okay? So the first thing is we're flipping a coin. So just like the previous problem, we have two options. We could get a heads or we could get a tails. Okay, so far so good? We doing all right? Okay, now we're gonna roll a die. Now this is a different problem than the previous one. And all of you told me as I walked around the room that there are 6 possible outcomes when you roll a die. So I flipped a head on my coin. And so now when I roll the die, I could get a 1 or a 2 or a 3, a 4. I'm writing too big, I'm sorry, or a 6. Oops, and that I wrote a 5 twice, so there's a 6. Or if I roll a tail the first time, it could be a 1, a 2, a 3, a 4, a 5, or a 6. So now what we've done is we've made a tree that allows us to list out all the possible options. So then the second thing is we're going to list out the sample space. I'm just going to abbreviate SS for that, sample space. And so here goes. So again, no particular reason. I have no secret motivation for this. I'm just going to start with the top branch. And so I've got heads and 1. That's the first outcome. Then heads and 2. That's the second outcome. Heads and 3. These are all the possible things that could happen. Heads and 4. And that is my purpose for doing a sample space. Heads and 5, and then heads and 6, and that exhausts the top branch. And now I'm going to move to the bottom branch, tails and 1, and tails and 2, and tails and 3, and tails 4, tails 5, tails 6. A little better? Okay. Well, okay, good. I'm going to flip the page. We're just going to do another one now. So we're just going to do these problems one at a time, each part one at a time. So I'm going to give you, 30 seconds, a minute, just depending on the problem for each of them. So example 5 says this. A radio station has 2 tickets to give away to Monster Jam, because who wouldn't want to go to Monster Jam? There are 4 finalists, and 2 of the names will be drawn from a hat. The names of the people are Christine, which we'll use the letter C for, Mike, the letter M, Larry, the letter L, and Phyllis, the letter P. So be careful when you become one of my friends, you become a name in one of my examples. So there you go. So A, determine the number of points in the sample space. Now, let me just let you know what's going on. We're picking 2 people from a hat. So when I pick the first name out, do I put that name back in the hat? No. Okay, so this is a without replacement. So I want you to make your best attempt at using the counting principle to determine how many possible combinations of winners can we have. Okay. So how many options are there when I pick the first name out of the hat? And how many options are there when I pull the second name out of the hat? Okay, so the key here is that I've got 2 tickets to give away. That's why I'm pulling 2 names out of the hat. So when I put my hand in the first time, how many possible names could I draw out? 4. And then you told me just a minute ago that I am not putting that name in. So if Christine's the name, Christine wins. Christine's name does not go back in the hat. She can't win 2 tickets. Okay. So now I put my hand back in the hat. And how many names are there possible to draw out now? 3. So that means there are 12 possible things that could happen in this sample space. Okay. With me so far? All right. Now here's what I would like you to do. I want you to construct a tree diagram that represents that. So again, your first set of branches are going to be all the possible names in the hat that first time. And then, depending on whose name was drawn out first, the second branch is going to be who's left in the hat for the second time. Okay? Give it your best shot. This is a difficult problem, I understand. So do your best. All right, well, let's see how you did. Because whatever you learn on this one, you're going to do this something very similar in example 6. Okay, these are two very similar problems, just because I want to reinforce what you're learning. Okay, so here's my seed of my tree right here. When I reach my hand into the hat the first time, what are the possible names that I can draw out? Okay, so Christine, I'm just going to use a C, and then Mike, I'm going to use an M, and then Larry, I'm going to use an L, and then I'm doing a terrible job of drawing this, so Phyllis is just going to be over here. We'll make it work somehow. I am a terrible artist, so anybody can draw better than me, I promise you, so sorry about that. And in fact, you've already seen this because I told you I can only draw pyramids upside down for whatever reason. Okay, so if I pull, the way this is going now, I'm going to cover up the rest. If I pull Christine's name out of the hat, whose name's left in the hat for the second time? Okay, so I'm going to do Mike, Larry, Phyllis. So I'm going to give you a second because I see a lot of you writing. So I think we may have cleared some things up. I want you to fill in the rest of the tree for the other 3 branches. So that means I draw Mike's name out. Who's left in for the second ticket then? And etc. Okay, so if I draw Mike's name out of the hat, who's left in the hat for the second ticket? Okay, C, L, P. I've redrawn my tree to give myself a little more room because the other one was going to end in disaster. So I pull Larry's name out. So who's left in there now? CMP, fantastic. And then finally, I pull Phyllis's name. So who's left? We've got CML. Great job. I don't know if you did this yet, but the other thing was to list out the sample space, all the possible things that can happen. So I'm gonna give you 20 seconds, follow the tree branches, and list out all 12 possible outcomes that can happen when we're pulling out these 2 tickets. All right, so the sample space looks like this. Again, I'm just abbreviating SS for sample space. So here we go. We could have C then M, C then L, C then P. Then we could have M then C, M L, M P. Then L C, L M, L P. And then last but not least, P C, P M, P L. Now, the reason this can be helpful to us is now in answering the last 2 questions, because now we know everything that can happen, and so we can determine probabilities. So you've got 2 quick probability problems you're going to do for me. The first one says determine the probability that Christine is selected. So we see that there's 12 possible outcomes. We determine that in the A part. Now you can go through and you can look at in your sample space how many of the outcomes have Christine in them. Then after that, you're going to go through and you're going to say determine the probability that Christine is selected and then Mike is selected. And again, you can go through and see how many times does that precise order of events happens, and you can construct the probability. All right, the probability Christine is selected. How many of the outcomes have Christine? Okay, so 1, 2, 3, 4, 5, 6. Those all have a C. Great job. So 6 out of 12. Just going to pop that into my calculator and it becomes 0.5. Or if you reduce the fraction, it's 1/2. Either way. All right, the next one says determine the probability of this specific event. Christine, I'm just going to use the letter C, then Mike. So that order is important. So we don't want the Mike, then Christine one. For whatever reason, we want to know that. And how many times does Christine, then Mike happen in my thing? Once. It's the very first one out of the 12. And I'm just going to leave that as a reduced fraction. You're welcome to make that a decimal. Let me write that down for you just in case that's what you did. So 1 divided by 12 is equal to 0.0833 if you wrote a decimal. 0.0833. Excellent. All right, well, example 6 is very similar. There's only one little difference when you're doing this and doing your tree diagram. Is this time in example 6, we're selecting 2 balls from a bag, and in the bag there is a red, a blue, a green, and an orange ball of some sort. And when you do this the first time, you're going to do this with replacement. Okay, so unlike our drawing the names from the hat, which was without replacement, we are going to, when we pull the ball out of the hat and we see what color it is, we are going to put it back in and it can be drawn again. So let's again just go one step at a time just to make sure we're all on the same page. So I'm going to give you 30 seconds. Do the A part. I would like you to use the counting principle to write down how many options, how many possible outcomes are we going to expect when we draw our tree. All right, we're drawing 2 balls out of the hat or the bag or whatever it is. How many options do I have the first time I reach my hand in the bag? 4. Great. Times. How many options do I have the second time I reach my hand in? 4. Great. Now notice, you may have looked ahead. After we're done with this problem, you're going to repeat the problem, and we're just going to do it without replacement. Okay, so the without replacement is going to be very similar to example 5. You're going to pull the first one out of the bag and you're going to look at it and then you're going to throw it in the garbage pail and you're going to then pull the second one out. So it's going to change things slightly. So this time though, you can expect that there's going to be 16 possible outcomes. So here's what I would like you to do. Do the B part, draw your tree and list out the sample space. Let me give you a couple minutes to do that. If you need me, if you're having trouble seeing it, raise your hand, wave it around. I'm happy to run to you and help you any way I can. Okay, so I just walked around class. Everybody seems to be doing this pretty good, so I'm just going to knock this out. We're doing this with replacement is the key. So my first time I reach my hand in, I could come out with red or blue or green or orange. And then when I pull the red one out, I'm putting it back in. And the second time I could have red or blue or green or orange. Same thing here, red, blue, green, and orange. Oops, red, blue, green, orange, and then finally red, blue, green, orange. Not the greatest looking tree, but it'll have to do for us. So I asked you to list the sample space. This takes just a minute because we've got 16 outcomes. I probably will not torture you with more outcomes than this. I just want to see if you can do this. I'm not trying to bore you to death. So when I do this, I've got red, 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 blue, red, green, red, orange. So red, 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 blue. And then blue, red, blue, 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 green, blue, orange. And then green, red, green, blue. You get the picture, I'm sure. And then finally, the ones that start with orange. So we got orange, red, orange, blue, best combination, orange, green, and then orange, orange. Better? Got that? Awesome. Great job. Okay, so then finish out. There's 3 probability problems. Now you got the whole sample space. Now you can identify the probability of those different events happening. All right, so for the C problem, how many times does the outcome RR happen in our list of outcomes? Once out of the 16 possible outcomes. 1 out of 16 is a perfect way to leave that, but if you wanted to make that into a decimal, then you made it into 0.0625. The next one, what's the probability that neither ball is orange? So how many no oranges do I have? Okay, I'm just gonna put a little check mark, just to confirm. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Excellent work, everybody. So 9 out of the 16. And then again, that is reduced already, but if you want to make it a decimal, then you got 0.5625. And then last but not least, that was no orange. How about at least 1 orange? How many at least 1 oranges are there? 1, 2, 3, 4, 5, 6, 7. 100%. 7 out of 16. Great job, everybody. So 7 divided by 16 is 0.4375. All right, last thing we're going to do, if you want to flip the page over or get a blank piece of notebook paper, I just want you to redo the first 2 parts, the A and the B part. What's the number of outcomes in the sample space? list out your sample space using a tree diagram if you do the same thing with the same color balls, but this time you're doing it without replacement. Okay, so just one more opportunity to practice. We're doing this one without replacing the first one that was drawn. Right, this time we're doing the problem without replacing the ball that was pulled out the first time. So when I do the counting principle, how many options are there the first time I pull a ball out? 4. I'm not replacing it, so how many are there the second time? All right, great. 4 times 3. So the number of outcomes changes to 12, very similar to our ticket problem. And so now I'm going to draw the tree diagram that represents this. So the first time I reach my hand in, there is a red ball, there is a blue one, there is a green one, and finally there is an orange one. But this time I am not replacing. So when I draw the red one out, what are the possible options with the second one? Yep, blue, green, orange. When I draw the blue one out, what's left is red, green, orange. Beautiful, well said. When I draw the green one out, I can get the, oops, that should be a red, blue, and green. And then finally, when I draw the orange one, I've got red, oops, I don't know what I'm doing. Red, blue, not green. We already drew the green. That should be an O. So that should be a red, that should be an O. So then when I draw the orange one out, I've got a red, and then I've got a blue, and then I've got a green. There's the green one that we wanted. So when we list the sample space, SS for sample space, we've got red, blue, red, green, red, orange. Then I've got blue, red, blue, green, blue, orange. Green, red, green, blue, green, orange. And then orange, red, orange, blue, orange, green. And there you go. And then if I had some probability problems, you could do the probabilities. But that is a pretty extensive view of tree diagrams.